All right, we're back again. Sorry about that. Okay, it looks like I've got to stay on this small screen. I was going to try to do the way I used to do on a bigger screen because it's easier to write, but I can't get back there now. So let me get my pen set up from here. Okay. Okay, we'd already done the criteria for differentiability, that f sub x is equal to 5 and f sub y was equal to 8y. Both of those are functions exist. They're of any open disk, then it's differentiable. Okay. The next thing is to find the equation of the tangent plane at AB, and that's what we were doing. It's going to be z is equal to f of AB, and we'd already done that. We said f of 2, 1 is going to be 5 times 2 plus 4 times 1 squared, which is 4. That would be 14. That's where that came from. We went through all this again. So that is 14. Well, let me write down what the formula is first. Okay. Z is equal to f at AB, that gives us a point to start from, plus your slope from there in the x direction, f sub x at AB, times x minus a, plus f sub y at AB, times y minus b. Okay? So this would be z is equal to 14, that's f of 2, 1, plus, now, f sub x at 2, 1, there is no x or y dependence there, so that's just 5. 5 times x minus 2, okay, plus f sub y at AB, well, AB is 2, 1, and there's only y dependence there, so that's just going to be 8 times y minus 1, okay. There's our equation for the tangent plane. Z is equal to 14 plus 5 minus 10 plus 5x minus 10 plus 8y minus 8, okay, which is equal to 5x plus 8y, and you have 14 minus 18 would be minus 4. Okay, so there's your equation for the tangent plane. Now, why in the world they wrote it the way they did? They start with the minus 4 and then do plus 5y plus 5x plus 8y. There's no reason to write it that way. 5x plus 8y minus 4 works just as well. Now, sorry it took so long to do something so simple, but it just got hung up and it would not budge from there. So I have to go back to this presenter view, which is very, very awkward to write on because it's so small. And that's why it looks like I'm writing bigger than I am, but I'm really writing smaller, but the screen that I have to write on is a tiny little patch, rectangular patch here on my screen, whereas before I expanded it to the whole screen. And it wrote well for a while and then just hung up, so I couldn't get it back. Okay, now they have a little blurb here on assumptions matter. Local linearity plays a key role, although most reasonable functions are locally linear. The mere existence of a partial derivative does not guarantee local linearity. This is in contrast to the one variable case where f of x is automatically locally linear at x equal a if the first derivative exists. The function g of xy of figure 6a, which is coming up next, so let's just go on to that figure. Let me blow this up. I think I can get it all on here. Just barely. bumping the borders in two places, but this is fine. Okay, here is a shape. Let's put it that way. The horizontal trace at z is equal to 0 consists of the x to y axis, and that's all, folks. Okay, this thing here, if you do a trace across there, you just get the x-axis here and the y-axis there. That's all. That's the only slice of that. Okay? But the graph also contains non-horizontal lines through the origin. Okay? Certainly the xy plane are there, but if you did a trace like that, you get that line. A trace like this, you get that line. You know, there's other traces you can do there. So the graph does not appear any flatter as you zoom in and zoom in and zoom in on the origin. It just doesn't happen. It's falling off one way in one direction, one way in another direction. It never flattens out, no matter how tight. It's kind of like if you got a piece of paper and folded it very sharply, say halfway the page, and then folded that again very sharply, and then sort of spread it back out and looked at it, you would have D's in two different dimensions there, and they're not going to be planar anywhere. No matter how close you get to the center of that, it's not going to be planar. The graph they show here is this one. G of xy is equal to 2xy times x plus y over x squared plus y squared. It seems like maybe we've seen this before. I can't remember for sure. But if you let x equals 0, y is equal to 0, you have an indeterminate form. Okay, so that's not technically defined at the origin. Okay, because you would have 0 over 0. Okay, can't have it, not defined there. But if you have, let's focus in on, let's just set y is equal to 0. Then the g of xy is 0. Okay, when y is equal to 0, g of xy is 0, because it would be 2x times 0 over x plus times x again, okay, over x squared, okay? So that would be, in fact, if we did that, let y equal 0 and let x vary. Now, I can't write on this. Hopefully you've seen it well enough. I'm going to shrink it back down now. And now it's not, there it goes. For some reason it wouldn't do it. Okay, g of x0 would be 0 over x squared. Okay, because everything goes. G of 0y is also going to be 0. Okay, and that's why you have your x and y axis are on your thing. But it can't be 0, 0 at the same time, so the origin, the function doesn't exist. Okay, so there should be a hole there. I don't see one in the drawing, but earlier we had drawings that were like that. So let's let let's see. Well, without beating around the bush too much more, the conclusion is this has what is wrong with this picture? Well, let's do, it's so hard to see because that's so tiny. G sub x, okay? G sub x would be the derivative of that with respect to x. Okay? I think I'll rewrite the thing here. It would be 2xy times x plus y times x squared plus y squared to the minus 1. Okay? So if we did the partial of f with respect to x, or g with respect to x here, that would be 2y times x plus y times x squared plus y squared to the minus 1. The second derivative of the first times the other two, plus the first, which is 2xy times the derivative of the middle one, which would just be 1 times x squared plus y squared to the minus 1, plus uh, 2xy times x plus y times, and this will be a minus then, minus x squared plus y squared to the minus 2 times another 2x, so that would be 4x squared. Okay? Now, does that derivative exist on some open disk D? Okay? Well, maybe on some open disk D, but not an open disk D that contains the origin. So therefore, you can't say this is differentiable at the origin, because that does not exist, because in every case your origin, your denominator would go to 0. You can't have that happen. Okay. I think that's, I don't know if that's what they were getting at, but that says it too. Let's go to example 2. Okay. Where is h of xy? Let's see if we can blow this up so you can see it a little bit better. Okay. Here's your h of xy, which is the square root of x squared plus y squared. The question is, where is that differentiable? Okay. Now, what I'm going to do is rewrite that again as x squared plus y squared to the 1/2 power. Okay? Well, let's take your h sub x. That's equal to 1/2 x squared plus y squared to the minus 1/2 times 2x. Okay, so these two go out. So that would basically be x over x squared plus y squared, square root of that. Okay? That is your h sub x. Okay? Now what's the requirement? It needs to exist and be continuous. Well, it exists everywhere except the origin. 0, 0 will not work there. Okay? So therefore, it is not differentiable on any disk that contains the origin. And you can kind of see that there. Any place here you choose on the side here, that'll be fine. No problem there at all. Okay? But you cannot exist any portion of the domain that would include the origin. Not going to work. at all. Okay? Same thing would do with your h sub y. Let's do that one too. H sub y would equal 1/2 x squared plus y squared to the minus 1/2 times 2y. And that would be y over x plus y to the minus 1/2. Okay, there is its derivative. The 1/2 disappeared when you did the 2y thing. So that basically gives you the same type thing. That is equal to y over the square root of x squared plus y squared. Neither one of those exist at the origin. They're not continuous at the origin. Okay? And neither is it differentiable there. Okay. That's, I think, all we have to do. Where is it differentiable? Everywhere except origin. All right, let's move to example 3, which I think this is the figure for. Find a tangent plane of the graph of f of x, y. Oh my goodness, wait a minute. We've just run over time-wise. And okay, I've lost, okay. We'll pick up with example 3 next time. That's where we're starting to end today. All right. I think I'm right there, yeah.